Hello folks, today I will be going over a linked list implementation in Python. I hopefully will be able to explain it well enough that you can basically translate this to basically any language. But the motivation here is actually something that happened a while ago for me when I was starting my journey into tech and going on job interviews and technical interviews. And actually one of the first technical interviews I had that basically delved into data structures and algorithms was a question I was given where I was asked essentially to implement a linked list, but I had no idea what that was. And so I eventually made a class that like wrapped a JavaScript list, which is like the interviewer was like saying, you're just kind of wrapping this data structure that already exists. You're not implementing it yourself. And I just sat there like, I don't know what you mean, because I just had no concept for data structures or this idea of a linked list. So I'm motivated to make this video to hopefully help explain what this concept is and show you an implementation, as well as one very common request on interviews, which is to reverse a linked list. So the first question I have here is, what is a linked list? Typically, we'll talk about a singly linked list. And basically, it's just a data structure that holds a linear collection of things or elements. And of course, order matters. And so here I have my little teaching board here to kind of explain it. So a traditional list will be implemented like this, where you have elements, in this case A, B, C, D, and E, as well as like an index representing their position. What we can do is reimagine this as individual elements that are housed within a fairly simple data structure known as a node. So a node object will house the value A, and another one will house the value B. And in doing so, the way we can start linking them up as a kind of like string of nodes is to have a pointer, the .next value of each object points to the next node in the sequence. And of course, you'll notice that the last node points to null because or none because that's the end of the sequence essentially. What a linked list is not that sequence of nodes. So that's one thing that might maybe throw people for a loop the first time they're learning about this, which is that a linked list is essentially like a wrapper for that sequence of nodes. What I'm representing here is actually not very common because each node is linked to the next node. All you need to really do is keep track of the first node. In this case, we call that the root node. And so this is typically how you would see a linked list implemented. You have a single root node, and if you ever need to grab another value in that list, you would just kind of follow it all the way down the line. And then the linked list object will house pretty basic operations. But I want to first implement a node class just to kind of get it out of the way. So here I am in a Jupyter Notebook, just kind of to showcase this. I will be sharing this, of course. I'm going to implement a really simple, basic node class. So say node, we'll init it, we'll construct it with a value, and so we'll just set self.value to whatever that value is, as well as a pointer to the next node, which at this point we'll just set it to like none or null. So that's our node class, and if I wanted to make a node, I would just give it the value maybe A, but that looks kind of messy, so I usually like to do a representation or rep r, and I need to return a string, which I'll make as an f string. Say, hey, this is a node, and it is this value. And so when I do that node, it kind of looks a little bit nicer to see what that is. So this is node A. I can say node 45, and kind of just shows up like that. What I'll do now is kind of go over some of the basic functionality of what a linked list will have going on into it, and then we'll actually start implementing those things. So like I said before, the linked list is a class. It'll wrap around a node, and it handles basic list operations. So first we'll have a variable called root, and that will point to the first node in the sequence. Then we'll have some methods like prepend, where we add a new value to the start of the list. Append adds it to the end of the list. There's also popping or removing. Pop will remove the first value of the list, and you can also pop at a specific index that removes the value at that specific index. I want to also do two kind of basic functionalities that we're maybe overlooking, which is like keeping track of the length of the list, which should be pretty simple, as well as being able to print the list in its full form. So let's go ahead and start building out the class called linked list. All right, we'll do init. I want to actually start it off without anything, and then we kind of add nodes to it. root will be nothing at the start. I'll also add a variable called length starting at 0. So whenever we remove or add elements from the list, we can keep track of it pretty simply there. All right, so let's again kind of create our linked list as an example. So it kind of looks messy, so I'm not liking that. So let's definitely do our another rep r, string linked list with the root being, and then I will say if self.root exists, then just return self.root, because it will be a node that has its own representation value. Else put none. I need to put single quotes there. So this is a linked list with no root, basically. That's what it's saying. Okay, so that's working. Let's go over some pretty basic functionality here. All right, so here we have some basic operations and kind of how we might go about doing those things. So let's say, for example, we have our original list like this, set up as I had before, and we call prepend, and we prepend the value z. So the first thing we'll want to do is create a new node with that value. So it looks like this. See that it has a null pointing to, because it doesn't know what to point to. Then we'll make sure to prepend it by assuming that the next value, the next node I should say, will be the current root node, because you're adding it to the beginning of the list. So it needs to basically come before the A. So we can do that first. So this is the kind of temporary situation at this point. So what we now need to do is assign the pointer of .root to that new value. And so this is our final updated list, and that's how it should look. So let's go ahead and implement that now. All right, so we'll call it prepend. It's going to take a value, and we're going to make a new node with that value. I'll also keep track of the fact that we are keeping track of the length, so we can actually do that here. So self.length, we're going to make sure we're adding 1. So we should always handle list length. One thing to keep in mind is if this is the first time that we're adding to the list, then root doesn't exist at all. So if that's the case, then we want to just assign the root to that and point to that node, the new node. I'm going to say assign to root if no root. So if not self.root, then self.root equals the new node, and we can just return because we're done. Otherwise, there is a root, and then we just need to do the thing that we just did in the example. So we need to add the current chain of node objects to the new root. Okay, and the way we do that is say new node dot next. You are currently going to be set to, and you're going to point to self.root, and then the new node becomes the root. And we do that by just saying self.root equals the new node, and it will do that swap. So let's go ahead and instantiate that. Let's run this. Okay, let's do ll dot prepend a. Okay, that ran without a problem. I can do l dot root, and I can see that's the a node for sure. If I wanted to, I can prepend again. Let's prepend www, and then ll dot root should be that www. Okay, and then the dot next should be the a, as it is. Okay, so I'm doing this, but I don't like doing this manually. So I think I'm actually going to implement our print functionality right now, just because it's kind of tedious to kind of keep going back manually. Okay, we're going to do print list. Okay, all this is doing is it's going to print the output to the console. And so what we're going to need to do is basically iterate through each node. But we need to start somewhere. So I'm going to say current node equals self.root. And while current node exists, we're going to print that value. So cur node.value. And then I want to then assign the next node, cur node equals current node.next. And when we get to the end, that next value is going to be null, and then the while loop will end. Okay, so let's run that. And let's do our thing again here. So I did, so that's all exists. So let's print. So at this point, there should be all these 4 W's and then an A next to it. So let's do print list. Okay, so that prints it kind of on top of each other. So if I wanted to add a bunch of things, so let's say let's run all this stuff again, and then print the list. See, it has this kind of weird format. I don't quite like that. So I think I'm going to modify the printing. So I know that the print statement here in Python, you can actually alter how it ends because at the end it actually does a new line. So you can say end equals, and you can set it to whatever you want. So in this case, I'll set it to a comma with a space so that it always ends with the comma. So that will help kind of separate things out a little bit. So let's see what that looks like. Okay, it looks a little bit better. I do have a weird comma at the end, but I don't really care about that. I just want to print it all in one line. That's fine enough for me. So that allows me to kind of see the whole list. So first it's a P because we're always prepending, right? So it's always going to the beginning. So this looks like it's working as expected. Let's check out the next functionality. All right, so the next functionality for the linked list is to append, meaning we're going to add a value to the end of the list. So how do we do that? Here is our original list. We call append with a Z, and then we'll need to create a new node. So that's what we're doing here. And then we need to do either two things here. And I'm going to go with option A here, which is to traverse all the way to the last node of our node sequence and then add it at the end there. You could also theoretically just keep a reference to the last node within the linked list instead of the root, which is the beginning. You could also keep a reference to the end as well, and you can handle that properly. If that's how you want to implement it, by all means, that makes things kind of easy. For this implementation, I think I like the idea of just reversing, just to kind of get used to that kind of code. And then we just assign the .next value to the new node that we have here. And so that's what we're doing there. All right, let's look at implementation. All right, so we're going to define append, and pretty much the same thing is true here. So I'm just going to kind of copy this code and just be lazy. Damn, why not? Because we're creating a new node and we're going to add to the length. Whatever we're doing, we're always going to be adding to the length anyway. And I think that pretty much the same thing is true here. If there is no root, we can just add it because appending and prepending are the same in that situation. So that code actually kind of looks the same. Here's where it gets a little bit different. We need to navigate to end of list. When we're navigating to the end of the list, what we want to do is not go to the next value always. We want to kind of keep track of the node before it becomes null, basically. So the way I would do that is to keep track of the last node, and we set that to the self.root while we're traversing it. And basically, I want to just break out of it the second the .next value is none. And so I can just do a while true, and that's okay to do because I'm breaking out the second we get to the end. If the last node .next is none, I can even say if last node .next is none, then we can break out, and then we'll know that the last node is the last node. Otherwise, we're going to just like keep traversing. So we'll say last node equals last node .next. And by the time we're done with this while loop, we will have last node as the actual last node, basically. And so all we have to do there is say last node .next equals that new node that we made. Okay, let's run that. And here we have a linked list. And instead of prepend, let's append. Do a bunch of these. A, B, C, D, E. Perfect. And if I print it out, I think I had an extra A from the last time I ran it. Okay, so A, B, C, D, E, it appends properly there. Also, let me just keep track. I haven't been really looking at it, but the length of the list should also be properly represented as 5. Yeah, okay. So right now we have a good implementation for adding to the list, either appending or prepending, as is typical. Now, another exercise I might leave to the viewer is to implement a kind of insert at index, which you can certainly do. I think once we go over the pop at index code, then you'll kind of be able to figure that out on your own. All right, so the first thing to remove an item is something called pop, and usually you also return the value back to the user who's ever calling it. So you will be returning a value from this method. So as before, I'm going to start with an original list here, and then we're going to call pop, and I will note here this is the same thing as if we were to call pop at index 0. So one thing to keep in mind here is that we will need to basically be really mindful of keeping track of our object references. All these node pointers and things can get a little confusing, but it's important to keep track of them when we are doing things like removing references or reassigning references. Kind of just keep track of everything if you can. So at this point, we're just going to keep a living reference to the root node. Since that's the thing that we're popping off, we're going to need to keep that in order to return the value. So at this point, just keep a living reference as a variable essentially, and the linked list isn't changing really at this point. And then what you'll do is then, now that you have a kind of handle on the root node, you will then reassign the root to that node's .next. And that's what it will look like now in this state here. But now that you have this living reference, you can now return the value. And what's interesting here is because this method will conclude, the existence of this temporary living reference will then disappear, and then this node, even though I know it's pointing to B, will actually get garbage collected because there's no reference to it anywhere. That's actually one of the reasons why we need to really keep track of all our object references, because once you don't, they get removed from memory. And once that actually happens, the actual linked list will look like this, and A will essentially disappear. All right, so let's actually code this up. First, we will define pop, which will self, not elf, self. We will first need to check to see if again, the root may not actually exist. So we don't want to pop if there's nothing left to pop. So I actually do want to kind of throw an error. So if self.root is none, then we actually do want to raise an exception here that communicates, hey, this list is empty. You're trying to do something that you shouldn't be doing. So I'm actually going to raise an exception saying, hey, this list is empty. I'm going to just like try that out here. So if I try creating a list and then do l.pop, it's going to say, hey, list is empty exception. Very good. Okay. So next we're going to do what I mentioned before about keeping a reference to the root node. So we're going to keep root object reference. I'm just going to call this like temp node self.root. Okay. Now what we can do is reassign root to next node. And so self.root equals self.root.next. Now, if this node is actually the last node, it's okay because the .next value is actually none, which is fine. You know, that's exactly what we expect it to be. So that's not going to cause a problem. Also, let's keep track of our length here, of course. So length, we're doing -1. And as I said before, we're, handle list length on that. And now we can actually use that temp node, now that we have that reference, and return the value back to the user. So we will return temp node.value. All right, so let's see here. Let's run that. Pop shouldn't work because there's nothing in there. So that's good. If I append all this stuff, that's our list of length 5. L.pop should pop off the A and return it. Perfect. And if I do the print list again, A is gone and everything is as it should be. So the next method we're going to go over is popping at a specific index. Again, you can use this to also do an insert at index if you really wanted to. Here's the idea. We're going to have our original list as usual. Let's call pop2. We're handling things with 0 indexing. So that's actually referring to the C. So this is 0, 1, 2. So the C is what we're trying to pop. We need to navigate the list until we get to that specific index. But the thing is, we need to keep track of the parent, because what we're essentially trying to do is kind of like skip over this value and have the parent, which would be B, have its .next pointer point to whatever C's .next value is. That way it kind of skips over C, and then we can just pop and then essentially pop it out and return that value. So we need to keep track of two things. We need to keep track of the previous node, in this case B, as well as the current node, which is C. At this point, we're just keeping track of pointers, so nothing is really changing about the linked list itself. And then what we'll need to do is reassign all of our pointers appropriately. We'll need to assign B's .next to D in this case, and we actually don't need to change anything about C. We just need to keep a reference to it so that we can return the value. And then we just return the value from C. And then same thing happens as before, because there's no reference once the method finishes, it gets garbage collected because there's no actual reference to it in existence. All right, so let's code that up. Pop at index. So this will need an actual index. And we actually need to keep track of a few things. So first, there's this idea of if the root is none, we are going to do a similar thing of raising an exception. And here's something I would like to do here is to create a separate guard method, which just kind of abstracts this idea, just kind of give it a nice name here, like validate root exists. And I'm just going to kind of bring this back up here because I'll be using this in more than one place, just to kind of abstract that. And that's all it does. It just raises an exception if there is no root. So now all I need to do is, instead of this, I can kind of cut that out, and then I can just call self.validate root exists. And here I'm just, throw error if no root node, and and I can just copy that and put that at the top of at this point, because whenever we're popping, we need to make sure there is actually a node to pop. One thing I also mentioned before is that if this index happens to be 0, then we might as well just use regular pop, because that's what that is. So I'm going to actually do that here as well. And since validate root occurs within pop, I can just do that right before this point. So if index equals 0, then we just call self.pop, and then we can return that. All right, there's another guard we need to do, which is this idea of an index being potentially out of range. So we need to throw error if index is out of range. So how does that happen? Well, we're not going to implement any like negative indexing, even though in Python that's a thing. I'm going to keep life simple on myself. So if the index is less than 0, that's a problem. Or if the self.length is less than index, which you need to think dot length is not 0 indexed, which index is. So we need to actually do like -1 just to keep things on the same scale. So we'll raise an exception, index out of range. Okay, so we did a lot of like validation and checking, but once we're past this point, we know that the index exists. The thing that we're trying to pop is actually in the list. So we can kind of like go forward with that assumption. Now what we need to do is keep track of two things, the parent and the current node. So as well as the index. So let's do that. So we need to get into the parent index position. So once we have the parent, we could always grab the child off of it since the parent has the .next, right? So we basically just need to position ourselves at the parent. And once we do that, we have both the parent and the current node, which is the .next for that. So let's keep track of our current position as well as the parent node, which is going to be what we're kind of like iterating over. So we're going to start with self.root. While the I is less than index, well, it's not that index, right? It's index -1. The reason I say index -1 is because we want the parent. We don't want to be on the actual index. We want to be one right before that index, which is why I say index -1 here. We want the parent node, not the child node. And then while we're here, we can just say, okay, the parent node, we're going to just iterate. It's the parent node .next. And then we make sure to keep track of our iterator. So once we're done with this while loop, we will have an index that is properly positioned at the parent. So that means this parent node is actually the parent node to the thing we want to pop. So let me just keep a reference to that. So pop node equals the parent node .next, basically is what I'm saying. Okay, so now what we need to do is now reassign the parent .next to whatever the pop node's .next is, which is again kind of skipping over that pop node, and that's all we're doing here. So let's keep track of that. So we reassign parents.next to skip over pop node, and it's literally just parent.node.next equals pop node.next. Now you might be wondering, well, what happens if the pop node happens to be like the last value, the last node? If that's the case, then the .next is none, and then we're just basically assigning the parent node to none because that parent node is now the end node. That's all that means. I just realized I haven't kept track of my length, so let's make sure to do that. Self.length -1, always handle list length. And then we want to return that reference to the pop node .value. All right, so let's see if this works properly. So let's run this, print the list. We got the right length, perfect. Let's see if we pop at index 1, which should pop the B. Uh-oh, it says pop takes, oh, right. I meant pop at index, sorry. Pop at index 1 that returns the B. Our list should now have ACD. And if I try pop at index 0, that should be, also I want to make sure that the length is now proper, right? Length should now be 4, right? Okay. Pop at index 0 returns the A, and length should be 3 now. Perfect. So print list. That's the CD. Yeah, okay, so that looks like it's working properly. All right, so at this point, we now have a working, functioning linked list. You might argue maybe there's more functionality I would add, definitely implement whatever you want. It's your linked list. You can do whatever you want with it. On interviews, obviously, you're going to be asked to maybe customize it or do something unusual or unique. And in the situation and with the context of that problem, you probably will have to implement something that's not this one, right? So definitely feel free to practice this, mess around with it. Now, one very standard typical coding challenge you might get is to reverse a linked list. So let's go over what that looks like, as well as kind of walk through how you might implement it. When we are reversing a linked list, what we're essentially saying is that the last node now becomes the root node, and the order and all the reference pointers are now like in reverse order. So for example, if this is our original list as usual, we call reverse, or we do some kind of reverse method or something, some function, something happens in the middle, and then we pop out with this as our structure. The linked list has the root as now E, and E points to D all the way up to A, and now A points to null. So in this way, we've actually reversed the whole thing. How do we do that? How does it even make sense? So here is what I'm going to propose to you. What we're going to need to do is be really careful about tracking our object references, and we're going to just iterate through each node while we're doing it. So here's what this looks like. I'm going to go as carefully as I can through this. Here is our node sequence. Node A, nothing's changed, obviously. We're going to have two references. A reference to the previous node. What I mean by that is the previous node that we have iterated on, which in this case is none because we're starting at the fresh start here, as well as the next node to consider. In this case, it's going to be node A because that's essentially like the current node to consider, but we haven't really done anything. This is just the initial state before we kind of go into our iteration. So the next thing that we're going to do is we're going to keep and store a temporary reference to the current node. In this case, A. The thing we're working on, keep a reference to that. So this is our current state here. Again, nothing's really changed about our actual node sequence. What we'll do next is assign whatever that next node is, which exists on the current node. We're going to keep track of that and say, okay, the next node is B. We need to keep track of that because the next time we iterate, we want to have that as a reference. We need to hold that reference essentially. Now that we have that reference stored, we can now kind of do our swapping because we basically have both objects. We have the A and the B. We can kind of now start doing whatever we want to those. And what we're going to do is we're going to assign the current node's .next pointer to whatever the previous node was. In this case, null. That might be a little weird the first time you're thinking about the iteration because we're starting with like null. How does that make sense? Keep in mind that our first node is essentially going to be the last node. So it makes sense that it points to null, the first, for the first node that we're iterating on. Once we've done that, we now have a very different node sequence state. We have like kind of this disjointed A and B that are now like kind of disconnected, but that's okay because we still have a reference to them in memory, to A and B, the next node and the temp current node. Now what we need to do is keep a handle on that previous node for the next iteration. So we now can assign the previous node to the current node, which is A. So what we'll do is have this reference to the previous node and the next node always like ready for the next iteration. So let's go to the next iteration and see what that looks like. All right, so this is sort of node B is now what we're iterating on. We're kind of considering what the state looks like. This is what our current node sequence looks like from last time, as well as the kind of previous state that we've had set up, which is the previous node being A and the next node to consider being B. And we do the exact same thing. All the steps we're doing here are now the same as before. We are going to store the current node temporarily as temp current node, which is B. We are going to take the current node's .next and store that as next node, which in this case is C. So that's what we've done here. Again, nothing's happened. Nothing's really changed in our node sequence. Now that we have a reference to both the B and the C in memory, we can now kind of do our funny business, which is to change the current node's .next pointer to the previous node, in this case A, which is now going to change our node sequence, which looks like this. Now the B and C are disjointed, but now the A and B are now kind of like linked up properly. And then in order to kind of clean things up for the next iteration, the previous node is no longer necessary because that's now attached to B. The thing we need to keep track is the B node for the next iteration. So we assign our previous node to B. Our next node is C. For the next round, we will now have both object references ready for the next implementation. So I'm not going to belabor the point here. I'm going to assume you kind of can see the pattern here. I'm just going to look at the kind of last node, in this case E, and see what that iteration looks like, just to kind of clean up what's going on. All right, so by the time we get to the last node, the E node, this is what our node sequence looks like. We have a reference to the D node as well as the E node. Again, we just do what we've been doing. We store the current node temporarily for E. we will store the next node, in this case null, for the next iteration, which there won't be one, but just keep that in mind. We assign the current node, which in this case E. The dot next pointer will now point to the previous node, which is D. So that's now like properly reversed. And we can assign the previous node to the current node, which is E. I'm only mentioning that because this is essentially how we can signify that we are now done. Our next node is null, so we know we're at the end. And what's nice is we have a reference to the previous node, which in this case is E. So once we're done with our loop, when we're iterating, we now have a handle for the last node, which by the way is now the first node. So once we're done with this, we can now assign the linked list dot root to that node. So let's see what that looks like. This is the current state of the linked list after we have done this reversing process. And mind you, we've only reversed the node sequence. The linked list currently has a reference of dot root pointing to the A node still. So that hasn't changed. So this is one representation if you're looking at it from this perspective. Another way you can look at it is like this, because all the nodes are kind of like pointing to this, the right. It's just pointing to the node, right? So if you do it left to right or right to left, it doesn't really change what's happening. So in this case, it's the linked list is still pointing to A at the end. That's essentially the last node. We don't want that, right? So what do? All we need to do now is to take our linked list and reassign the dot root value pointer to that last node, which if you remember was coming from the previous node, which was stored from our iteration process. So this is what it will look like now that we've reassigned it, or more properly, like this. All right, so let's implement this and see what this looks like in code. Okay, so what I'm going to do here is implement a function right now just to kind of like get that out of the way, but I will in the end add this reverse method to our linked list implementation. So let's call this reverse node sequence, and we're going to be given a root node. So the two variables we're going to keep track of is previous node, which we're going to initialize with none or null, and the next node is going to be kind of like that root node. So that's the node we're going to consider next. And while there's a next node, we're going to be iterating. Mind you, once we're done with the list, next node will be none once you get to the last node, and that will exit the loop properly. First, we need to store. And all these steps need to be in this proper order, mind you. Store the current node temporarily. I can't spell, okay. And we're gonna call this temp current node, which is the next node. Then we need to store next node, which is called next node, which is the current node's dot next value. So I'm just gonna copy that. Oops, copy that dot next. Then we have to assign current nodes dot next pointer to the previous node, because that's like reversing. Now we can start doing that reverse process. So we got the temp node dot next is now pointing to the previous node. We're basically going to do this last cleanup step, which is to assign the previous node so that the next time you iterate, you will have a reference to the current node. And that's what we just say prev node equals temp current node. And once we're done with this while loop, we will have reversed the node sequence, and I will return the previous node just to kind of see what that looks like. So how do I showcase this? So what I'll do is I will implement my linked list here, which has, it currently is housing a node sequence, right? So if I look at the linked list.root, that's the root node that has A, B, C, D, E, right? So what I could do is then pop that into our reversing function and see what we get. Okay, so it returned E, that means the previous node. So if I look at the root, it should now, because now it's like the last node really, that should not have a dot next value. Yeah, so it doesn't have anything. And node E, which I don't have a reference to, actually, I should have maybe stored this value. That should be, now the beginning. Okay, so what I'll do now is just kind of go up here to my fabulous looking linked list. I'm just going to copy this whole thing and bring it down here. And I'm just going to kind of copy this whole function. I just want to add it to my class, the linked list class, so that it can reverse itself without too much hassle. So I just need to do a little cleanup here. First, I can just call it .reverse because that won't conflict with Python's innate reverse functions. And it doesn't need any input. It takes the root node, which is self.root. I think all the other variables should stay just fine. And I'm not returning anything. So here, I now need to reassign self root to previous node, to last node, which equals previous node. Okay, so yeah, we're not returning any value. We're just going to assign self.root to that last node, which is called previous node. All right, so let's run that. All right, so let's see if our new linked list implementation can actually get reversed. So we'll create that. Here's our list, length 5, right? Okay, so let's see ll.reverse and see if it got reversed. Print list, it got reversed. Look at that. Okay, so this is working as expected, and I gotta tell you, when I took that interview, it felt so bad not even understanding something that seemed like it was supposed to be like basic understanding. So hopefully this has been a good learning experience for anyone who's watching. I will go over one last thing, which is this idea of a doubly linked list, which you may also hear about. The doubly linked list is essentially the same thing, but instead of the node having a reference to the .next, it also keeps a reference to the previous node. And so it looks something like this, where each node has, obviously a reference to kind of two things. The doubly linked list is a little bit easier in terms of implementation. For example, if you need to pop something at a specific index, then you don't need to worry about the parent. You just kind of just go to the index because you have a reference to everything. So it makes implementation a little easier. What's not great though is that each object now has twice the reference. It has one more reference, right? So it actually takes up more memory with that implementation. To be honest, what seems to me like a lot more hassle, because now you have to keep track of two references every time you pop something or add something. You have to keep track of two things now, or I should say four things, because it's on the index itself, but also the previous and next. So you have to keep track of those as well. It's kind of a bit more of a hassle, but you will probably hear about it, and it is something that you might want to consider. So I am not going to actually implement that in this case, but that is another exercise for the viewer. If you want to try it out, definitely give it a shot and see what you can do with it. All right, folks, if this content is something that you enjoy, please make sure to subscribe, do all the good things, and I will see you next time.